Now fourth one, air enters a duct at 10 degrees, 80% relative humidity, flow rate is 2.5, volumetric flow rate 2.5 meter cube per second. It is steadily heated at constant pressure of 1 bar. So now it's around the atmospheric pressure. As it flows through the duct and the temperature increases to 30 degrees, no moisture is added. So this heating, no moisture is added. So what it means is the specific humidity remains constant. Changes in potential and kinetic energies are neglected. The specific gas constant and the Cp for air are given as 1.005 and 0.287 kilojoule per kg Kelvin. Determine the rate of heat transfer and the relative humidity at the exit. Okay, so we will solve this problem using the formulas and steam tables. First, mass conservation. Here, the dry air entering as a mass flow rate of Ma1. Okay, that remains constant. It comes out. So I can say Ma1 dot equal to Ma2 dot equal to M dot A. That is for the dry air. For the vapor, MV1 equal to MV1 dot equal to MV2 dot. Again, there is no removal or addition of the moisture. So that also I can keep as MV. That means omega 1 equal to omega 2. So what is omega 1? Omega 1 equal to M dot V1 by M dot A1. This is M dot V2 divided by M dot A2. So this is constant because no moisture is added or removed. Okay, now I can write the energy balance. What is the energy balance here? Heat transfer is there, no work interaction, that will be equal to, I will say M dot exiting things, M dot A into HA2 plus vapor also is going out with its own enthalpy at the state 2 minus M dot A into HA1 plus M dot V into HV1. So that is the conservation. Please understand that the mass of dry air into its enthalpy. Obviously, this enthalpy can be calculated by Cp into T. Similarly, here mass of water vapor into its enthalpy. How will you get this enthalpy? This is from the steam tables. So HV2, HV1, etc. we have to get from the steam table. From the corresponding temperature, we can get the saturated vapors enthalpy and substitute here. Okay, so now this can be rearranged as M dot A into HA2 minus HIA1 plus M dot V into HV2 minus HV1. Now I can write this as M dot A times Cp into T2 minus T1 plus M dot V into Hg at T2 minus Hg at T1. Now I can use the omega's expression. So I will write this M dot A, I will take it out, Cp into T2 minus T1, okay, plus omega times Hg at T2 minus Hg at T1. So this is the value. So now I have to find what is M dot A. What is M dot A? M dot A will be equal to density of the air. Okay, and at the entry, we will say at the entry or inlet into volumetric flow rate at the inlet, that is given. And it is steady flow, so it remains the same, but you have to find this. What is rho A1? That will be equal to PA1 divided by R into T1 into So you can say I. That will be entry pressure, partial pressure of air at the entry into the temperature here divided by R into Ti. Okay, now this into volumetric flow rate of air. So Vi, V dot I. Okay, so how will you find the PA1? PAI will be equal to what? PV1 equal to 5 into Psat at T1. Okay, what is given here is basically 10 degrees 80% relative humidity. So 10 degrees is T1, Phi is 80, so Phi1 is 80%. From that I can find PV1, that is equal to 0.8 into, this will be 1.23 kilopascal. Again from tables corresponding to 10 degrees I will get the value of Psat, that is the saturation pressure. So that if you substitute, I get this as 0.984 kilopascals. So what is PA1 then? PA1 or PI will be equal to P minus PV1, which will be equal to 99.016 kilopascals. So now I got the TI, so from that I can find the mass flow rate of the air. So what is mass flow rate of air? Will be equal to 99.016 into 10 power 3 divided by P by R, 287 into 273 plus 10. So that is equal to into volumetric flow rate is 2.5 meter cube per second. That will be equal to 3.0477 kg per second. So that is got. Okay. So now omega is known. Omega 1 already we have calculated, or you have to calculate. So omega we have to calculate. Omega will be equal to 0.622 into PV1 divided by PA1, which is equal to 0.622 into PV1 is basically 0.984 kilopascals divided by this is 99.016. So that gives you omega 1 as 0.00618 kg vapor divided by kg dry air. So this will be equal to omega 2. Okay, so omega 1 will be equal to omega 2. So I call this omega. So that is got. So m dot a is got and omega is got. Now HV1. HV1, as I told you, it's Hg at T1. So from the tables I get this as 2520 kilojoule per kg. Similarly, HV2 will be equal to Hg at T2. Okay, T1 is 10 degrees. Okay, T1 is 10 degrees and T2 is 30 degrees. It's all given in the problem, so that you get the value of HV2 is saturated vapors enthalpy, specific enthalpy at T2. That will be equal to 2556. So all the values are known. Now you calculate the Q. Q dot will be equal to 3.0477 mass flow rate of air into Cp is 1.005 into T2 minus T1, that is 30 minus 10 plus omega 0.00618 kg vapor per kg dry air into 2556 minus 2520. That is HV2 minus HV1 into omega. Mass flow rate of dry air is multiplied with all these terms. So finally I get this as 61.94 kilowatts. That is the rate at which heat is basically removed. Heat is added. Sorry, heat is added. So the temperature increases from 10 degrees to 30 degrees. Okay, now finally PV2 will be equal to what? PV2 equal to PV1 we have already seen, because omega 1 equal to omega 2. So that will be equal to 0.984 kilopascals. Okay, now what is Psat at 30 degrees? From the table I get this as 4.25 kilopascals. So that means Phi2 will be equal to PV2 divided by Psat, which is equal to 20.984 by 4.25. That comes out as 23.15%. So this is about a problem where sensible heating, it's called sensible heating, no moisture is added or subtracted, and I go from a particular value of dry bulb temperature to another value where the temperature increases. So we can indicate this in the chart. So now what you do, you go to the state 1, which is given as 80% relative humidity 10 degrees. So 10 degrees line is this, 80% relative humidity is this. So go here. That is the state 1. Okay, this is say state 1. From that I go to state 2, but constant omega line. State 2 is here, the 30 degree line. So I can first draw a line here slowly. This is the one, and 30 degree line comes out here. So it will be somewhat here. This is the state 2. That's all. So this is the process. Sensibility constant omega, dry bulb temperature increases from state 1 to state 2. Now I can find all the properties. So need not do so many calculations. So what is the for example, what is asked here is Q, we have to find the enthalpies, to find the Q, correct? First what we will find is say relative humidity at the exit state. From this you can find. So this is 20 and this is 30. So obviously 25 line is here. So I can say it is about 20 to middle of this. So 23, let's say 23% relative humidity we have got by calculating 23.15, correct? Then I can find the initial omega. Omega is from this you can find straight away. Humidity ratio 5, this is 6. So 6 point, this is 7. So I can say 6.1 something. That is 6.1 grams per kg of dry air. What I have got from the calculation is basically 0.00618, that is 6.18 kilograms per this. So again that is also fine. So now enthalpy, you have to take the enthalpy. This is 25, this is 30, so this is say 25.5. So I will say this H1 star equal to 25.5 kilojoule per kg dry air. Okay, now from this is 45 and 46 I can say, 46, 47, this is 47, so this is 46. So H2 star will be equal to 46 kilojoule per kg dry air. Now Q dot will be equal to mass flow rate. So Q dot will be equal to m dot A into H2 star, because it is dry air base. So I want the mass flow rate of dry air into this. That's all. Already this enthalpy incorporates the vapors also corresponding to the relative humidity and specific humidity. So I can straight away do this. But m dot A, how will you find? M dot A can be found as V dot A into rho A, or V dot A divided by VA at 1 okay into H2 star minus H1 star. Now V dot A is given in the problem as 2.5 meter cube, but VA1 we can take from here. So for example, this is specific volume of dry air. Okay, so you can see that at the state 1 we want basically volumetric flow rate, the state 1 is given. So this is 10 and this is this is 0.82, okay, and this is 0.8, okay. So this is 0.85, for example, this will be 0.85. So I can say it is 0.81, this is 0.81, so this will be 0.805 approximately in the middle. So I will say this has 0.805. So if I calculate this, basically 2.5 divided by 0.805, I'll get 3.05. So then if you substitute this, you get the Q value. So you can see that the values can be taken, all the calculations can be made based upon the chart values. But anyway, the accurate retrieval is required. So you have to use some scales and accurately you have to require, and basically these curves are converging, etc. These are all straight lines. So you have to very carefully select the point and take the property values and substitute. So no need to do many calculations. Anyway, the heat calculation anyway we have to do. Okay. So these are the this is done because of the fact that the pressure is around the atmospheric pressure of 760 mm of mercury. I can use this chart. This is about this problem. So fifth problem now. Calculate the amount of heat removed per kg per second of dry air if air from 35 degrees centigrade 70% relative humidity is cooled to 25 degrees centigrade 60% relative humidity, which actually steadily flows through a cooling section. Any water condensing will exit at 25 degrees as saturated liquid. Okay, actually exits. Okay, so now given data, T1 is given as 35 degrees centigrade, Phi1 is 0.7, 70%. So that can be defined as PV1 divided by P sat at 35 degrees centigrade. So that implies PV1 will be equal to 0.7 times 0.0563, which is equal to 0.03941 bar. That's taken in bar. Now total pressure P is 1 bar. So that means I can find PA1 as 1 minus 0.03941, which is equal to 0.9606 bar. So now omega 1, the specific humidity at the state entry state will be 0.622 into 0.03941 divided by 0.9606, that will be equal to 0.02552 kg vapor divided by kg dry air. Now state 2, T2 is given as 25 degrees centigrade, Phi2 is given as 60%, so that is defined as PV2 divided by P sat at 25 degrees. So that comes out, PV2 will come out as 0.6 times 0.0317. So that will be equal to 0.01902 bar. Here PA2 will be calculated as 1 minus 0.01902, which is equal to 0.98098 bar. So omega 2 can be calculated as 0.622 into PV2 divided by PA2, which is equal to 0.01206 kg vapor divided by kg dry air. Okay, so these calculations are made and states are fixed. Now mass conservation. For the dry air, what is entering? MA1 will be equal to m dot A2. I can just say MA. This is also can be taken as 1 kg per second, because per kg per second we have to evaluate everything. And for the water vapor, I will say the mass coming in is m dot V1 and mass leaving will be equal to m dot V2 plus some amount of water is also leaving, m dot W. Okay. From that I can calculate m dot W will be equal to m dot V1 minus m dot V2, which is equal to m dot A times omega 1 minus omega 2. So that is the mass of the liquid water which is removed. So now obviously I can see that the omega 1 is 0.02552, omega 2 is 0.01206. So this decrease in omega is found. So what some liquid will condense and go out as saturated liquid at 25 degrees as given in the problem. So now energy conservation. Here I know that Q dot equal to m dot A HA2, the outgoing stream, plus m dot V2 HV2, this is dry air, this is water vapor, plus some water is also going out, I will say HF2, minus incoming stream m dot A HA1 plus m dot V1 into HV1. Okay, so moisture is coming in, no liquid is actually coming in. So, but after condensation, the liquid goes out at the final temperature. So, now rearrange this m dot A into HA2 minus HA1 plus m dot V2 into HV2 plus m dot W into HF2 minus m dot V1 into HV1. So, this can be written as taking m dot A outside, Cp into T2 minus T1 plus omega 2 into HV2 plus omega 1 minus omega 2 into HF2 minus omega 1 into HV1. So, we know all these quantities, but we have to take from steam tables. HV1 is nothing but Hg at 35 degrees, the entry state temperature, that will be equal to 2565 kilojoule per kg. Similarly, Hv2 will be equal to Hg at 25 degrees, which will be equal to 2547 kilojoule per kg. Hf2 will be equal to the Hf at 25 degrees saturated liquid, which is 104.9 kilojoule per kg. So, these are all taken from steam tables. Okay, now I will find Q equal to 1.005 into T2 is 25, T1 is 35 plus omega 2 is 0.01206 into 2547 HV2 plus 0.02557, that is 0.02552, that is the omega 1, minus omega 2 is 0.01206, this into 104.9 minus omega 1, that is 0.02552 into HV1. HV1 is 2565. So, when you evaluate this, you get as minus 10.05 plus 30.7168 plus 1.4119 minus 65.46. 46, which is equal to minus 43.65 kilowatts. Okay, so this is the heat just transfer out of the cooling duct, so that the air is cooled from 35 degrees to 25 degrees and some condensation occurs. Final relative humidity is 60% and the initial is 70%. So now we will go to the psychrometric chart. Because the average pressure is 1 bar, you can use this. So as I marked the states here. First state is 35 degrees, relative humidity 70%. So relative humidity 70% line you have to take here, this is the one, and 35 degrees here. So you have to carefully take the state 35 degrees. So this is the one. Okay, here it comes actually. Here. Okay. So this is the state 1. Okay. Now you see that the state 1 35 degrees and the relative humidity is 25 point, you can say, sorry, specific humidity is 25.5 grams. We also got what? 0.02552, correct. So we also got that 0.02552, that is 25.5. So again, that is the state 1 here. What is the enthalpy? Enthalpy is here 101 you can take. So this is 101, and state 2 is here, that is 25 degrees and 60% relative humidity. So this is state 2. So we can see that here you can get the value 10, 11, around 12 we are getting 12. We also got about 12 only, 12 grams, that is 0.01206 we got. So this is about 12 grams. So approximately the states are indicated here. Enthalpy at state 1 is, as I told, 101. For state 2 it is about 55. You can say 55 or 55.5 something. So you get the difference is, the first law is Q dot equal to m dot A into H2 star minus H1 star. Please understand that this H is given per kg of dry air directly. So just multiply by this. Now I know m dot A is 1. So 55. So Q dot will be equal to 1 into 55 minus 101. So that is approximately 46 kilowatts. So what we got is also 44. So we can just 2 steps we can do this in this. So accurately locate the state 1. Okay, this is 70% and 35 degrees, and state 2 is 25% and 60 degrees, and retrieve the enthalpy values. Whatever additional thing what you want, you can retrieve that. So this is about the thing. Obviously, you can see that there is a decrease in the specific humidity and decrease in the dry bulb temperature. Okay.